Good afternoon, everyone. I'm Simran Joslal, and I'll be your host today for today's Laser Talk session. It's my pleasure to introduce our speaker, Dr. Lars Hildebrandt, Director of Sales at nanoplus. He has been working in the tunable semiconductor laser market since 1996 with extensive experience spanning product development as well as sales and marketing, particularly in external cavity diode lasers and quantum cascade laser systems. Dr. Hildebrandt holds a PhD in physics from University of Potsdam, Germany, where his research focused on blue external cavity diode lasers for atomic spectroscopy of indium and gas sensing applications using laser spectroscopy. So between 2005 and 2008, he worked as a project manager in automotive industry, contributing to product innovation and high volume series production. He returned to the semiconductor laser domain in 2009 and has since been leading global sales and marketing activities at nanoplus. Today, he will be speaking on mid-infrared tunable laser diode technologies for high sensitivity molecular spectroscopy. In this talk, he will explore advancements and applications of mid-infrared laser technologies in enabling precise and sensitive molecular detection. So, and if you have any questions during the session, please feel free to drop them in the chat box along with your email IDs. We will try and do our best to address them during the session if time permits. Otherwise, we'll get back to you via email afterwards. So everyone, please join me in giving a warm welcome to our speaker, Dr. Hildebrandt. Dr. Hildebrandt, thank you for taking the time to be with us today. It's truly a pleasure to have you as part of Laser Talk series by Laser Science. Over to you, Doctor.
Yeah, thank you, Simran, for the kind introduction and giving me the great opportunity to talk here. I'm just sharing my screen.
Yes.
And you should be all able to see now my screen. And I have a laser pointer. Yeah, I hope you can hear me very well. So as Simran already said, I have quite a lot of experience in tunable diode lasers in general, and spectroscopy. So the title of my talk and introduction is today mid-infrared. So we are mainly focusing on the 3 to 6 micrometer area. Tunable, so the lasers that I'm talking about, they can change their wavelength. Laser diode, which means they are very, very small technologies. There's different kind of technologies I'm introducing, and all these mid-infrared tunable laser diode technologies are used for high sensitive molecular spectroscopy. So quite a lot of already here in the title, mid-infrared tunable laser diode technologies for high sensitivity molecular spectroscopy. So this is what it is about. This is the finger of my boss. And as you can see here, this is the little chip he has on his finger here. So most of the, or all of the things I'm talking about today are from this little chip. And if you enlarge the chip with a microscope, you can see it looks like that. And the main functionality of the semiconductor technology is just below this little straight here. This is called a ridge. I'm going into a little detail more later, but just to introduce it. So if you enlarge this with a scanning electron microscope, you see this structure here, which is the ridge and the grating. Coming to this back later. And if you even go further into detail in the atomic or crystal structure inside here, with the, you can see the crystal structure here on the left side, it's indium arsenide, and on the right side you can see aluminum antimonide on the right. And here you can see this is 1 nanometer. So all this is going pretty very small. You need a lot of technology to realize this. Someone has his microphone on, so maybe you can turn your microphones off so it's not got disturbed too much. This is the house, one of the facilities here in Gabrunn in Germany that we have with a little clean room here. And this is the other house just here. I don't have a picture of that. I always wanted to make one, but the sun doesn't shine as nice as it does on this picture here always, so I didn't make a picture. We have more facilities here. We have a second site in Meiningen. So the first site here is in Würzburg. The second site is in Meiningen. This is Germany. So here you can see this is Berlin. This is Hamburg. And we have some new facilities also very close in Würzburg, a daughter company, Sensorlight Technologies. So in total, we are about 150 people now. Here you can see almost the whole company in our 25th anniversary a few years back. This is our CEOs, Dr. Kurt and Professor Forchel. It's one of the traditional family-based companies, one of the hidden champions. So here, for example, this is the son of Professor Forchel. And I cannot see the daughter of Professor Forchel. She is working in my team. Also, this is the daughter of Professor Forchel. It's another daughter. And this is the wife of Professor Forchel. And here's the other two kids of Professor Forchel, of Johannes Kurt. And here is my son also working in the company. I'm not on this slide because I was visiting a customer in China, I believe. When everybody else is a party, then I have to work, unfortunately. But this is also very nice sometimes. Just briefly, a little bit of the company. So the philosophy that we have is a really full vertical integration. So we start really with the material design, simulation, and then we do the epitaxy, which is the growing of the crystal. Then all the device processing, like mask aligning, the E-beam to structure the grating, and scanning electron microscope. So it's very technical. Then the device mounting is mostly done by robots. And then here on the final slide, you can see the robot is doing the burn-in and the characterization. And my colleague, she only has to feed the robot to, and the robot is doing everything else. So this is the way we can keep the process simple, high-end, and still cost-effective. And going along the products that we're selling and that we're developing, but I'm focusing mostly on technology. So these are the different technologies that we can do for finally then the last slides of my talk. I'm talking about markets and applications, but first I'm concentrating on technologies. So the DFB lasers are at every wavelength between 760 nanometer and 14,000 nanometers. And we use different technologies here. So let me start with the DFB lasers. So DFB semiconductor lasers can be produced between the lowest wavelengths is 760 nanometer and about 3 micrometers. We use normal diode laser technology. Then we have a technology interband cascade lasers in the mid-infrared. So this is the main focus here, between about 3 and 6 micrometers. And then quantum cascade lasers, they start at 6, even a little bit lower, and go up to 14 micrometers. They have a large tuning coefficient, relatively high power, many custom-specific solutions to get to every wavelength, and then various packaging options. So you can only have the chip. So this would be the chip here on a carrier, chip on sub-mount, we call this. We have little TO housings. You can get these fiber coupled. This is a little collimator inside here, or this is a high volume manufacturable mount, which we just recently released, where customers which go into higher volume, like at least a few hundred per year, have a quite cost-effective and easy to install, easy to use mount for these lasers. That is the core of tunable diode laser absorption spectroscopy. Here is an example for water vapor. So what you can see here is the laser chip. So we grow, this is the substrate, and then we grow the crystal, as I showed in the first few slides, in this direction. And the red one here is the active zone, where the electrons are changed into photons. So everywhere where it's red, you can create photons out of electrons. Then on top of that, we are etching a ridge. This is called the ridge with the gold cover. So the electrons flow from the gold through the crystal into the substrate and then away. Inside this ridge, you have this front facet and here the rear facet, and you have a standing wave. And the standing wave can be, of course, different modes. And the grating is selecting only one of these modes, and every other mode is not lasing. So you have a single mode laser, only one wavelength, which you can see here, for example, this red line, which is going over the spectrum, which is the wavelength change. When you change the current here, the wavelength is changing. And at the same time, of course, you also get more power, because all you need to change is the current in this case. And if you change the current, it changes the wavelength, as you can see here. And anytime the wavelength hits one of these lines, absorption lines, the water vapor molecules start to vibrate or rock shake or whatever they do. And that is one specific mode of that particular molecule, which is like a fingerprint. So you can exactly see, is water vapor available? Is water vapor in my gas, or is it not? If there's no water vapor in my gas, this would just be a straight line. But with water vapor, you can see these absorption profiles. So that's the core principle of tunable diode laser absorption spectroscopy in the example of water vapor. So please keep that in mind, how it works when I go through the rest of the presentation. There's different laser concepts available. So if you go down here to the 700 nanometer range, we're using gallium arsenide or aluminum gallium arsenide chips. Then going further up the wavelengths to higher wavelength, you can use indium phosphide or gallium antimonide up to 3 micrometers. Then between 3 micrometers and 6 micrometers, you're using interband cascade lasers, ICLs. These are type 2 transition. And then here, the quantum cascade lasers, they really go down to 3 micrometers, but we only use them above 6 micrometers. I will come to that in a minute. Up to 14 micrometers. So with these 3 technologies, normal diode lasers, interband cascade lasers, or quantum cascade lasers, we can cover the whole spectrum of wavelength between 700 something nanometers, 760 up to 14 micrometers. So one good question I got asked many times is, why do you have interband cascade lasers when the QCLs go down to 3 and the diode lasers go up to 3 as well? So interband cascade lasers are not really needed in that particular picture here. That is absolutely true. Let me explain why. A little bit into technology, so I'm really digging deep. So to explain to some of the nerds in the audience what the difference is. So I got asked many times, what is the difference between these 3 technologies? So the normal bipolar interaband diode lasers, they are diode lasers. You can see here the valence band and the conducting band in your energy scheme. So, and the radiative recombination is between the conducting band and the valence band. So the electron jumps from here down there and a photon is emitted. So that's a normal diode laser. You can do diode lasers down to something like 300 nanometers up to 3 point something nanometers. You can even squeeze that up to, I believe, 6 or 7 micrometers with lead salt lasers. But in that case, you need a lot of cooling down to liquid nitrogen. So to go to higher wavelength, the quantum cascade lasers was developed and invented in 1994 by Jerome Feist group. Here you can see the transition is only happening in the conducting band. So the electron jumps within the conducting band, within the same quantum well, from an upper state to a lower state. emitting a photon. So this has a lot less energy than this transition. So here you can go up to terahertz regime in principle. So the interband cascade laser is like a little bit of in-between technology. So the electron here, the quantum wells are formed here in a kind of a W shape, and the electron jump here from the conducting band upper state to the lower state valence band, but the valence band is within this, from the energy level of the valence band is still within the conducting band. So you can reuse this electron again. The electron is tunneling again into the next stage of the cascading laser. So in this case, the electron is lost to a hole. In these two cases, the electron can be reused. If you want to get more into detail, these are the papers here. And I will provide a link to this presentation later to Laser Science. And if you want to have that presentation, then just please write them an email and you will get the presentation from Laser Science. So I'm coming to what can these lasers do at the different wavelengths and why are they used for spectroscopy? So the lasers, as I said, are single mode, as you can see here. This laser only lasers at 2,334 nanometers. And you see the side mode suppression is something like 45 dB. So you only see really one line. And this line can be shifted in wavelength with current. So if I'm setting the laser to 30 degrees, would be this line. And at 40 milliamps, it would be 2002 nanometer. And if I go up to something like 140 milliamps, it would be 2005 nanometer. So about 3-4 nanometer of tuning, where this line is tuning. This is the little red line that we've seen on the other slide, which I ask you to remember. And here you don't have any CO, so you don't see any absorption lines here. And the same counts for methane, ethane, here at 3,345 nanometer, tunability, and the PI curve of the power curve. Also in this case, you don't see any absorption lines because they are not present while we did this PI curve. So when you look at the mid-infrared area, say between 2 and 8 microns, you can see the diode lasers are here between 2 and 3.5 micrometer. And the quantum cascade lasers are starting at 3, going up to 8 and even beyond. The change that you can see here in this graph is the threshold power density. So the diode lasers at 2 microns, they have a threshold power density of something like 0.3 kilowatt per square centimeter. And if you go up here, they are in the order of something like 10 kilowatt per square centimeter. Going to the QCLs, all the chips, all the lasers are in the order of 10 or several of tens of kilowatt per square centimeter. That means if you want to run a QCL, you have to cool them a lot. So normally it's 1, sometimes even 2 stages of TECs, of coolers needed. You don't need to cool it to liquid nitrogen, but you need to cool it excessively. There's a lot of heat which is wasted because the power threshold density is so high. And the ICLs, the interband cascade lasers, they are again down here in the area of 1 and below kilowatt per square centimeters. So this is the reason why they can be used in handheld system, they can be used at room temperature, and they just need temperature stabilization, but not temperature cooling. Why can we only use them up to 6? Well, if you go to 7, you have to change the material of the interband cascade lasers. And here they are also again in the area of 10 kilowatt per square centimeters, same as the QCLs, having the same problems as the QCLs. So that is the reason why we only really sell them between 3 and 6. There is a paper from us and our partners in Vienna. I'm not going into detail. Maybe this spot will be down to here in the future. We don't know this yet. This is still under investigation. So that was the DFB lasers, right? So you have the tunable diode lasers. They can be they have a grating on both sides of the ridge, which make them small bandwidth. And with that, you can tune them. You can use the same technology as you can see here without the grating, and then you have these many, many modes. So this is called a Fabry-Perot mode because you have Fabry-Perot laser diode because you have a Fabry-Perot modes within this cavity between the front and the rear facet. I'm just going very quickly into that, so just 1 or 2 slides to show you can turn them up much further. While in the DFB lasers, we work with currents something like 100 or 200 milliamps. Here you can have 6,000 milliamps, so 6 amps of current running through that laser, giving you a watt of output power. But as you can see here, it's not tunable, it's not single mode, this is just a power source. So this is not a tunable laser. I'm just checking this here because we have some customers who are using these kind of lasers for amplification of tunable lasers. Or you can use this with an external cavity to make it single mode. I'm not getting into detail. If there's questions, then please just ask me. Then the next technology is SLD. So also this is laser material, but you have the ridge in a certain way tilted so that you have an angle here, Brewster angle here, and there's no reflection and no standing modes. So this makes it a very broad light source. Also here, just one slide, very broad light source, only a few milliwatt of output power, because this is not laser amplification. But these parts are used for photonic integrated circuits. And they are coupled to the photonic integrated circuits, and then the feedback from the PICs, from the photonic integrated circuits, they will make the laser, make it lace and work in a single mode, and then it can be used for tunable diode laser spectroscopy as well. This is just one slide. I'm having a few more slides for the LEDs. They are not lasers, but it's a very interesting, quite new technology to have LEDs in the infrared. The emission is very broad, right? So you can see here at 4 or 5 micrometers, you have an emission which is something like 800, what is it? 800 nanometers in that range emission, and only 1 to maybe up to 10 milliwatt of output power. It's a small package, so this is a €2 coin, but it's the little package which you can see a picture here, and this one is the LED itself. It normally has 640 micrometers by 640 micrometers and emitting through CW at room temperature, quite high power, and at wavelengths between 2 micrometers. We can even go a little bit further, up to 6.5 micrometers. That is also used for spectroscopy. It's not for high resolution spectroscopy, but that could be very cheap. So we have the broadband source, the gas cell, a filter, and a detector. And this is called NDIR, non-dispersive infrared spectroscopy. It's been widely used if the light source, if the whole sensor has to be extremely cheap, but you don't need high selectivity and you don't need high sensitivity for the gas. Also with this, we have done some improvements. So here, just a quick slide, up to 10 milliwatt of output power. It's a world record that we did back in 2019 for this kind of interband cascade LEDs. They can be produced quite large. So this is 640 by 640, the normal standard of our LEDs. And here you can see a small LED. This is just a pitch of 80 micrometers by 18 micrometers, of course, giving a lot less power than this high, this large LED. So this is just to show that we can customize things whatever the customer requires. Also here, the wavelength can be shifted. The 10 micrometer LEDs are at 70 Kelvin, right? So they are at liquid nitrogen temperatures. Nevertheless, you get light at 10 micrometers. This is needed for some applications, but the excessive cooling, of course, is quite expensive. So you cannot use this, of course, in a very low-cost system. And here's some little tricks we do with the IC LEDs. So it's called a resonant cavity interband cascade light emitting diode. Here you see the stages of the cascade, which is also here. And the light is then traveling through this grating structure. So it's a quite large grating structure here, which is giving a feedback into the stages. So some of the modes are suppressed. It's not as highly suppressed as in a laser, but it's suppressed. And here you can see the cavity response in blue. And this would be the emission from just the ordinary LED. And if you combine the emission of the ordinary LED, the 5 stages that I showed, with the cavity response, you will get a smaller bandwidth light source, right? So combining these two results into this black one. That is again the standard LED, and if you combine it with the grating, you have a small bandwidth LED. So that can be used for some higher resolution applications. And those are also tunable or dual color, as we call it. So everything from here to the left is the same like in the resonant cavity LED. And now you take a little silicon growth on top of that LED, which makes the cavity longer. And if the cavity is longer, then the wavelength is shifting, of course, to a slightly different wavelength. And as you can see in this slide here, this is 2 color LEDs. They are from the same growing process. One of them, this one here, has a little silicon on top, and the other one doesn't have that silicon on top. And you can switch between them. And so you can see the light is switching about something like 100 nanometers away to a different wavelength. So if the gas you want to detect is here at this one, you can be on gas, off gas, online, offline very quickly to make a low cost system. Yeah, we also that was the main product lines. We also do custom packaging, collimation, some technology development, etc. So if there's anything in that range you want to develop or you need, then please approach the colleagues from Laser Science to contact us. What you also need is a detector. So not only the light source, but also you need to detect the light. And normally when you can emit light, the same technology can also detect light. This is what we did. So this is called an ICD, interband cascade detector. Just quickly, there's 2 technologies, gallium antimonide and indium arsenide antimonide. And you can see here the cutoff for the first is somewhere at 6 micrometers, and the cutoff for the second is here somewhere at 8 micrometers. So that would be a nice replacement for the MCT detectors. They work at room temperature, and this kind of technology can be used. We use it ourselves for our own purpose. We don't have it as a product at the moment because we're concentrating on lasers, but also this is possible with that kind of technology. Coming back to tunable diode laser absorption spectroscopy. So this is the slide I explained. Then one of these lasers, they look like this, right? Very small bandwidth, and not like this. And the question here is that one laser, just going back, this is not 18 DFBs. This is one single device, right? So we have a technology where you can tune this single mode laser, like step tuning, go from here to here and so on, to make it a very wide bandwidth tunable laser. That is used for very broad absorption profiles. So the gases, the small molecules I was talking about, for example, water vapor, they have a very small absorption profile, only something like, I don't know, 0.3 nanometers or something in that range. But if you look here, for example, at blood alcohol, they do have these features in blood, like these absorption profiles here. So if you could go with a laser over these absorption profiles from 1.5 micrometers all the way to 2.5 micrometers, then you can have this absorption profile and detect how much alcohol is in the blood of the driver. That is possible with an FTIR, but you cannot install an FTIR into a car. So we need to have some laser technology. And this 18 wavelength emission lasers that we had was incorporated here at 1.7 and at 2.3 micrometers inside this little button. It's a start button, and it measures, so this start button here, and it measures the alcohol that is in the human. And if it's too much alcohol, then the car will tell the driver, I'm sorry, you're drunk, you cannot drive. Unfortunately, that was not finished, this project, due to some presidential change in the United States, who stopped a lot of projects which he didn't like. So this project is on hold at the moment, but we're using that kind of technology also for other projects. Another way of creating many lines at the same time to go over a large absorption profile is using different lasers. So what you can see here is, I think it's 9, how many is it? I don't know. Different lines, and they are coming from the different lasers. So this is a laser, this is a laser, this is a laser, this is a laser. They're all DFB lasers, but at slightly different wavelength, as you can see here. And they're sitting on the same bar. So it's the same growing process, but we are writing different gratings. As you can see here, this is the rich. We are writing the grating differently on every chip. So every chip here has a slightly different wavelength. And they're sitting here on this little mount, one bar here and the other bar down here. And they are targeting different wavelengths here on that absorption profile of glucose. In this case, it's glucose measurement for diabetes patients, for non-invasive laser-based sensing. So you don't have to drill blood from the patient. You just have to, the patient just have to put this instrument onto his arm, and then it measures the glucose content in the patient. Yeah, I'm coming to different markets. I hope I was able to show you the technology already. So I want to spend another 10-15 minutes on different markets and applications that our customers and users are using. The main driver is process control. We also have some defense applications. Safety is very, very big. So you want to know before it's exploding that the area is getting dangerous. There's a lot of ongoing for environmental detection, some medical applications, and then, yeah, our friend on Mars here has also a laser. That is for research and development. So the first application that we had was from a close cooperation with a company called Spectroscopy. They are now owned by Anderson Hauser, and this is the instrument. So the laser sits up here, and the light is going down here and up again. There's a little mirror down here to the detector. You can see there's 2 lasers, one here, and they are detecting water vapor in gas pipelines. And you can see here, this is in the Mojave Desert, so the lasers and the systems are sitting in the very, very hot, only covered by this little shade here. And I think this is Mojave Desert here. And up here, you can see it's the same instrument in Alaska, in the north of the US, where it's sitting in the very, very cold. This is for gas spectroscopy in the process industry. In this case, the laser sits on one side and the detector on the other side. This is the stack. in that case, they're detecting SO2 inside this stack. There's also other gases, but they want to know how much SO2 is in that gas. So they have the laser and the detector on the other side. And you can see they're looking here at this small line here, somewhere 4 micrometers. And this is a good example. You can see here water vapor and other gases. They have large absorption lines at other wavelengths. Here you can see the wavelength. But here at 4 micrometers, there's not so many gases, so you can have a nice detection of SO2 at 4 micrometers with this technology. That's from our customer Neo Monitors in Norway. They also do the same thing for hydrogen. So here's a little experiment that they set up to demonstrate putting hydrogen here into that gas flow, and they detect hydrogen also with tunable diode laser absorption spectroscopy. You can detect methane and ethane at the same time. For example, Aerodyne research in the US, they're detecting here ethane within methane. And if you plot the ethane and the methane in this kind of plot, you can tell whether the gas is coming from a landfill, a compressor, or gas liquids. Just by the amount of methane in that, of ethane in that methane, you can tell the difference. Classical example is methane pipelines. They have a lot of them in the US and also in China. So the little pipelines, they go to every house for cooking and for energy. And these pipelines sometimes have little leaks, and there's PSI and Heath consultants. They have this car with a little sensor on here. It contains an interband cascade lasers, and they drive around the cities, and it's automatically mapping an alarm when they see a leak. Breath gas analysis. So this is isotope selective CO2 measurements for liver healthy by a company Argosmed in Germany. I'm just clicking through it rather quickly. This is measurement of oxygen in food packages. So if you want to know if your food package is tight, in the old days you have to put a needle in the food package, which means it is not tight anymore. So you cannot make 100% measure all the packages. So here the laser is shining into the body of the food package, and some of the light is reflected into this into the spectrum to the photodiode. And with tuning the lasers, you can tell, is there any oxygen inside the package or not? So if there's oxygen inside the package, then it's not tight. A good example here for safety is coal mines in China. They have the problem that if something happens, if a fire occurs, then these conveyor belts will transport the fire throughout the whole coal mine, and that is extremely dangerous for the workers and also for the technology, for the equipment which is in there, of course. So they are installing at the moment CO sensors made with interband cascade lasers in many thousands of installations to detect fire, to have an early fire warning based on interband cascade lasers. Yeah, this is another slide for a package, so to say. So the package in this case is this little baby here. And the laser shines into the lung of the laser, and some of the light is reflected to the photodiode. So the doctors can, with every breath, tell if the oxygen that is pumped into this early born baby is used by the lungs and going into the baby, or if they have to do something without drilling blood from the baby all the time, and be extremely accurate on oxygen consumption. Yeah, some fancy applications in space. That is always, of course, the highlight. We have a laser on Mars and the Mars Science Laboratory since 2012. So this instrument is called SAM, S-A-M, and one of our lasers is inside SAM to detect CO2 and water vapor on Mars. So that was very exciting a few years back. That led to other applications in space. So at the moment, I think we have 10 or 12 lasers on ISS. I don't know how many they are really, to detect different gases. In this case, it's formaldehyde, but they're also detecting CO2 and methane and other gases in International Space Station. We are on satellites. So for example, on Sentinel-5 satellites, it's a European satellite. There are 7 lasers on every of these satellites when they incorporate these systems, right? So there are 6 on that one here and another one on another instrument on that satellites. They're mainly for calibration purposes, so they don't detect these gases. The gases are detected by the instrument, which is a spectrum analyzer, but the laser calibrate the spectrum analyzer in that case. Yeah, and we have a laser far away as well. It's not on Mars, but Artemis is running at the moment. They successfully went around Moon, I think yesterday, and will be landing back in a few days. And our lasers are in the capsule. They are inside the breath instruments that the astronauts will wear on Moon. So they don't have it with them at the moment. And also on the landers here and on these instruments. So everywhere where you have people, there will be some of our lasers in that breath analysis system to detect CO2 and oxygen in the breath of the astronauts. Okay, so yeah, I think that was also what was about it. I was just checking how I'm doing in time. So we have 20 minutes. I would just quickly go through these industry corporations. They will be on the slides just to show you how many things we do with partners. So if you have a development project with us or with some, I don't know, international corporation, please contact us. We cannot tell anything, right? So if we have a large corporation with one of the major companies of this planet, of course, this is not something we can advertise. But these are the projects we're doing with European Union, for example, or German projects. This is for medical process, for arthroscopic measurement. This is high sense infrared sensor. This is where we develop the detectors and miniaturizing everything. QCL sensors, so many QCLs in an array to detect different gases, having a wide tunable. Then what I showed here is there oxygen inside the package, and this should be done, of course, with a little handheld system, which you can just approach to the package and say, okay, this package is tight. This is quantum cascade lasers. That's quite interesting here with our partners in Italy. University in Bari in Italy. They have a huge project where they want to have different gases measuring in drones, in cars, or in the environment, like cities. This is again food. Here we have a little, so you can see this is the ridge of the laser, and you can see how small this lens is. It's like a little mirror. So this is directing the light and collimating the light away from this plane. So we can have 4 or more lasers in the same light path. This is not a project, right? So all these are just at the moment research and development projects. Yes, so with that, I hope I was able to show you some of the technologies that are used in that field. Here you can see a little drone load. So the drone will be up here, and this is flying around, shooting to the Earth, and the reflection will be collected by this instrument, detect how much methane is in the air. So that was a cooperation between us and Fraunhofer. Yeah, thank you for your attention.
Yes, thank you,
So,
Dr. Hildebrandt, for sharing your expertise and valuable insights. So, would you like to address some questions on the chat box? And if anybody has any questions, they can actually ask. We have left with a few minutes, so.
I have got few questions in chat. Can you read that?
yeah, I think I can go through the chat. And maybe I just go through the chat first and answer the questions. So the first question is, how do you make edge gratings in DFB lasers? So they are done with the electronic beam lithography.
Okay.
Right? So we're putting the unfinished parts into the machine. They are coated and by a layer of active material, and then this is structured by the E-beam, and then it's etched down by a normal etching process.
Okay.
So the structuring is done by an E-beam.
Okay.
You know, what details of class of clean rooms? We don't really have a high-end clean room like you would have in computer technology or so, because most times all the machines are working in vacuum, right? So we do have clean rooms. I think they are 1,000 parts per 1,000 class or 10,000, but yeah, well, I think it's 1,000. It's not high end needed.
Yeah, still it is very good.
Yeah, it's good. We try to keep it clean, of course, right? So and we don't open the windows there, but it's not needed for most parts because yeah, as I said. Then you had a question, epitaxial growth. Yeah, it's MBE. So we use molecular beam epitaxy. We don't use MOCVD. We have two types of MBE. One is with solids, and one is with gases.
Okay.
And I think we have 4 MBEs running. MBE, that's a question I get many times. Why don't you use MOCVD? Because you can have higher throughput, right? So I think that's the background of the question. We don't have high throughput, right? So we can grow something like a 4-inch wafer. We can grow 2 4-inch wafers per day per machine, and on each 4-inch wafer you can place something like 100,000 chips, right? So we can make 10 million in a year or 20. So when the MOCVD comes into account, for us this is at the moment not a problem at all. And why do we use MBE and not MOCVD? Historical reasons. We have always been using MBE and we know how it works. So you can do the same thing with MOCVD. No difference. There's many groups who use MOCVD. Okay. How tunable is achieved? Do you know the Vernier tuning? So the question here is the 18 DFB slice. How is the tunability achieved? Yes. There's 2 gratings in that laser, and if you combine these 2 gratings, you can shift them just a little bit. It's called Vernier tuning.
I know. Vernier effect. Yeah, I know.
Yeah. Okay, perfect. Yeah. Okay. I have a paper for that. So if you write an email to me or to Laser Science, I can send
nowadays,
it.
Like in semiconductor laser, people use the Vernier effect for large tunability, right?
Yes.
This Torrent also uses that for some. I remember some laser which they use the integrator for FBG integrator. They use a very large. That is, what is the model? ST7000 something. Anyway,
I don't know exactly, but yes, the Vernier tuning is widely used.
Yeah, I know this thing. Okay. My last question was, which gases can be PPT or PPB or PPM? Any guidelines or what?
It depends on the length of the absorption, right? So in principle, you can do PPM or PPB or PP trillion with every gas, but you need to have a long absorption line, a long absorption length, right? So if you're just using a small length, like, I don't know, 20 centimeters, then of course you don't get parts per billion, you get parts per million maybe, right? But if you're using cavity ring down spectroscopy, or if you're using a very long length optics, then you can get higher parts, a higher resolution of parts per million. I was not focusing so much on the different technologies here that are used with these lasers. I was really focusing on the laser technology itself.
Thanks. Very nice talk. Very nice talk.
Thank you. Thank you. Thank you. Let's see the other questions. Do I have any more questions here? Yeah, share the full talk. I will provide a link to Laser Science, and then they can spread around the link to everyone to download. Can you tell us about the fiber cup? Should I answer the other questions, or?
Yeah. Yes, sure. We have 10 more minutes, so I think I'll be okay.
Okay. So can you tell us about fiber coupling with a free space of DFB lasers for gas sensing? Well, the difference is just in one case you have a fiber, and it's easier to put the fiber to different positions and to collimate that. So for an experiment, a fiber is widely used. For an instrument, my customers don't use fibers because they are expensive. They want to have a free space DFB laser, which has also a little bit more power because the coupling efficiency of the fiber is pretty low, to use it for the instrument. So I'm not sure if that is the background of the question, but you can get the laser fiber coupled or free space as you want. But fiber coupled is a lot more expensive, and it's not scalable in price for volume. The next question is, sir, can you please explain the detection limit of the sensors? Yes, I also said in the other question, I'm not doing the sensors. I'm doing the light source. But the detection limit is depending on the sensor. For example, the sensor in the coal mine, that is only parts per million, right? You don't need to know how much CO is in your is coming from the fire. You just need to know, is this a fire or not? And then if you look at the instruments from what's the company in the US, Aerotech, I just don't remember the name at the moment. They have parts per quadrillion, which they have a very, very long, I don't know, 200 or 300 meter of path lengths, multi-pass cell inside to be very, very sensitive, to have an extreme low detection limit. So that depends really on the instrument. Then I have a question here. I don't know what's. When you talk of tuning, does it mean you're able to tune the wavelength over a wide range in a single diode? If so, how is it achieved in principle? If you have a single diode and you have the grating on both sides of the ridge, and you have a Fabry-Perot mode formed inside that ridge between the front and the rear facet, and the grating is selecting one mode out of the many modes from the Fabry-Perot resonator, and this mode is lasing. And if you now want to change the wavelength, you're changing the current of the laser chip. And the current of the laser chip is changing the temperature of the crystal. And if the temperature of the crystal is changing, this is changing the refractive index of the material. And if the refractive index of the material is changing, this is changing the wavelength. So it's a temperature effect. Why the SLD gain medium is placed diagonally? This is when you have a diagonal ridge, then the light will not go directly 90 degrees onto the surface, but with an angle, like a Brewster angle. And if you go to a surface with optics on the Brewster angle, that means that there is no reflections. So that is a natural anti-reflection coating. Like underwater, if you have a flat surface, you can look through the water without total reflection. So this is to avoid reflection. Then the next question: can you please give us more information on breath analyzer application installed in the car? What I showed is a blood analyzer, not a breath analyzer. There's also a company doing a breath analyzer. I don't really have more information. Dr. Makar, can you explain what you exactly want to know there, maybe?
Hi, thanks for giving me the informative talk. A couple of questions were, I could see that there was blood analyzer as well as breath analyzer. So we in past have done some experiments on using QCL based detection for trace gas sensing. So I was just thinking what kind of sensor and all, because this requires a parcel in the whole apparatus. So without that, the person is exhaling, and how you can quickly sense that. So that was basically my curiosity to know what exactly has been done. And second, I wanted the information on SLDs. I've been using extra loss and superlume SLDs for almost a decade or so. So I just wanted to know this, how this nanoplus SLDs bring to the table, whether they are more stable, their bandwidths, how they are good in the bandwidths. Like I am interested in 840 nanometers or little longer. So what kind of bandwidth is possible and how they are priced in comparison to superlume or XLRs?
So for the breathless analyzer, this is a multipass cell. You're detecting CO2 in different isotopes. And I think it's a 100-meter multipass cell. Maybe it's 30 meters. I'm not 100% sure, but that is they use a multipass cell. And they have to clean the gas and the breath gas so that there's no water vapor coming into that cell. The SLDs, they are similar. We can offer wavelength that other companies cannot offer. Right, so customers come to me when they want to have 2.3 micrometer SLD or whatever wavelength, and we can also tailor the SLD to the application. Right, so the large companies, they just do one kind of SLD, but we have a very huge flexibility of really customized SLDs which really fit into the photonic integrated circuit of the customer. Right. It's not a standard SLD. When you have a standard SLD that you can work with and that is working perfectly fine for your experiments, then our service, I would say, is too expensive. But we found with many customers that this is not the case. So they want customized parts. They want parts which fit into the experiment. They want different wavelengths. Sometimes they want 3-4 different wavelengths, but all from the same kind. And because we have the whole platform, we can be very flexible there in combining this.
Do you mean multiplexing of different wavelengths is possible onto a chip? Like if I need some, let's say 4 different wavelengths.
It's 4 different chips.
Yeah, 4 different chips can be put into a single chip, integrated into a single device.
We don't do the device. We do the chips. We're a chip fab, right? But our customers
about this coupling into this photonic integrated circuits. So on board, is it possible to create source as well as some other components required for some?
Yes. Yeah. We have customers doing exactly that. They're getting in one case 2 different wavelengths, in another case they're getting 4 different wavelengths, and they integrate that into the same. I'm not 100% sure. Maybe this is 2 by 2. Maybe that's 2 different photonic integrated circuits. That I'm not 100% sure of.
And what is the smallest form factor you can offer in SLDs? Are they butterfly package or they are even smaller than
No, you can have chips. So you can have them as chips.
But still, I would appreciate if you can share me some. I put my email ID. So if some information can be shared, some data sheet or some product profile.
Absolutely, yeah. Please contact Laser Science or contact us directly if you have questions there.
Coordinating from Laser Science, I have dropped in my email ID above. So,
yeah. Please. Yeah, please.
Thank you.
Great. Yeah, I'm looking forward for the discussion. Yeah. And the last question I have here, is it possible to get the laser above 40 microns with QCL technology? Yes, this is possible, but not from us. We just stop at 14 micrometers, but there's vendors for QCLs in the terahertz range. Yep, that was it from the questions from the chat.
Okay, thank you, Doctor, for addressing all the questions. It was lovely having you. And I thank everyone for attending as well. In case anybody has any more questions, you can always get in touch with the team, and then we can email the answers to you. So thank you very much. Jagdish sir, was your questions answered?
No, I'll just wait for it. I can send an email to Lars anytime. Yeah.
Okay, perfect. Sorry, I just noticed your question right now. I'm sorry.
Okay.
Okay, perfect.
Yeah.
I will send you the link with the talk just now, so you should have it in 10 minutes or something, and then you can use that to spread to whoever is interested. Yeah, thank you very much to the team and for everyone for listening, for the great opportunity. And
Thank you, Lars.
have a great day.
Thank you.
Thank you.
Thank you, everyone.
Bye-bye.
Thank you.
Thank you, Lars.
Bye.
Bye-bye.
Bye.